plus 10x, close parentheses, raised to 1 over x.
Okay, perfect. Good. So like any limit, we have to see what this is. So where is e to the x going when x approaches infinity?
To infinity.
Perfect. Of course, 10 to the x is still approaching infinity. Look, this is not an indeterminate case. This is not infinity minus infinity. That's an indeterminate case. Infinity plus infinity is infinity. And now we have to identify the power. Where is the power going when x approaches infinity?
0.
Yes. So this is one of the powers, the indeterminate case. We have 3, we have 1 to infinity, we have 0 raised to 0, and infinity to 0. So these are the most cumbersome. Good. So we have a long step, a long list of steps here. I wish I could say it's a 2-step procedure, but it's not. It's an infinite step procedure. Okay, so first of all, if we remember, this is my page 4. 2? Yeah, yes, okay. So we have to denote the function e to the x plus 10x to 1 over x. Then we have to apply natural log to both sides and bring already 1 over x, because we've done this so many times. But if you want to write the intermediate step, you can, of course. Then we apply limit to both sides, although this is not what we want, but we will get there slowly but surely.
I have a question.
Yes?
So when you bring the 1 over x down, you didn't have to subtract anything from it, the power?
Oh, let me show that intermediate step. So when I apply natural log here and natural log here, the property of log says natural log y is natural log y. Natural log of this expression is natural log of x to a, which means a natural log x. This is the property.
Okay, thank you.
Sure. So then we put 1 over x in front and then natural log of x, or all this. So now here I have natural log of e to the x plus 10x divided by x. Okay, so at this point, we have to check again because I don't know what this is. Initially, it was a power, but now it's a ratio. So I'm hoping for infinity over infinity or 0 over 0. Why am I hoping for infinity over infinity or 0 over 0? Why am I hoping for these two, one or the other? That's my hope, but why?
So you can apply L'Hopital's rule.
Brilliant, thank you. So of course we already know that this approaches infinity, and limit of infinity is infinity, and this is infinity. So I have this situation. I don't have to do anything else, just directly apply L'Hopital's rule. Limit as x approaches infinity. I will differentiate the easy one, and you will differentiate the difficult one. Can anyone tell us how to differentiate natural log e to the x plus 10x? Yes, 1 over e to the x plus 10x times
times e plus 10.
E to the x plus 10. Awesome. Okay, great job. Excellent. Thank you. Good. So now we have limit as x approaches infinity from e to the x plus 10 over e to the x plus 10x. Yes, of course, it's still infinity over infinity. Can anyone differentiate the top? And the denominator.
E to the x.
Yes. And the denominator?
E to the x plus 10.
Very good. Okay, there is no need, but let's continue. So limit as x approaches infinity. Can anyone differentiate top and bottom again?
So e to the x over e to the x.
Perfect. And how much is e to the x over e to the x.
One.
Perfect. How much is limit of 1? Limit of 1. Very good. Remember, now we copy the beginning and we copy the end. So then I have limit of natural log y equals 1 as x approaches infinity. And under continuity, we are swapping the operators. So we have natural log of the limit as x approaches infinity of our function equals 1. Natural log of what is 1? What could this be so that the natural log is 1?
To E.
That's it.
8 to,
Or e to the first power equals that. Same thing.
Can I ask one quick question?
Yes, of course, any.
If you scroll up real quick, it's kind of like an algebra question.
Yes.
So, before you went to the right array, that last line where it says limit x approaches infinity, 1 over e to x plus 10. So you just multiply e to x plus 10 to the denominator and the numerator?
Very good question. If I have 1 over a times b is the same with 1 over a times b over 1, 1 times b, a times 1. One over a times b. 1 over a times b. It's not 1 over a times 1 over b, which will be 1 over ab. This one does not have a denominator. Or if you want, it has a denominator 1. So it's 1 over a times b over 1. 1 times 1 is 1 times b is b, and a times 1 is a. But because it was 1 in the denominator, I disregarded that, so I wrote e to the x plus 10 over e to the x plus 10x.
Okay.
Does that answer your question?
could you,
Yeah, I think so.
and could you re-explain the last step, please,
Here,
of the swapping? Yes.
after the swapping,
Yes.
or the swapping?
The swapping, like, I'm a bit confused on like how you would write that like straightforward because it's kind of like broken apart. So is it like starting from the indication of you swapping, that's what our response would be?
Yes, because
be nice.
remember, yes, let me refresh your memory on one of the limit laws. I will just pick one. So we had the limit as x approaches a from the square root of f of x. This is the outer operator, saying the tendency of this, and this is the inner operator. Because the function is continuous, I can take the square root operator outside and make it the outer, and I can take the limit inside close to the function. This is maybe easier to see. This is exactly what we did with the limit as x approaches infinity from natural log y. And now the inner operator, instead of being the square root, is the natural log. So I will take the natural log and make it the outer operator, and I will make the limit the inner operator. It's the same process. Now the inner operator was the square root, and here is natural log. And now this became the outer, and this became the outer. See, in both situations, the limit is the outer, but now it became the inner. Here, the inner was the square root, and here the inner was the natural log. They were the inner, but now they became the outer. So this is the swapping of the operators. The correct sequence is apply natural log and then apply limit. But it also works if we apply the limit first and then natural log to it. And this is allowed from chapter 2. And it's the swapping of the operators based on the limit laws and based on continuity. Is this better?
Yes, that's fine. Could you go back to the paper of the solution?
Right. And then we solved this equation. This is a log equation. And we had the following. Log base a of x is y is equivalent to, we wrote this a long time ago, a raised to y equals x. A raised to y equals x. So what we had was that the limit of natural log of y as x approaches infinity was, it was natural log of the limit as x approaches infinity of y equals 1. So I have the natural log or log, it doesn't matter. The base is e. So I'm using this. E raised to 1 equals this. E raised to 1 equals this. E raised to 1 equals this. So then that's why this is e. From the property that any log equation can be changed into an exponential one and vice versa. So this was a log equation. E raised to 1 equals the inside. E raised to 1 equals the inside. That's how we get that. And that's why the answer is E. Is that better?
Yes, thank you.
Yeah, this is a very, very important property. That any log equation can be replaced by an exponential, and any exponential can be replaced by a log. Very good questions. I have no doubt that you studied, because otherwise you wouldn't ask these questions. That makes me very proud. Thank you. Next question. Anything else? Now, anyone else? Anyone has any questions on any of this? Anyone? Okay, we're ready for the next question.
Okay, I have another question.
Yes.
And it is.
And I think I'm on page 5. Yes, page 5.
It was on 4.2, 16, number 16.
16, you said in 4.2?
Mm-hmm. Part of the homework.
Yes, we are ready.
Okay, it's f of x is equal to x cubed minus 3x plus 2.
X cubed minus 3x plus 2?
Yes.
Okay.
And then we have the f is continuous on -2 to 2.
So are we asked to apply Rolle's theorem or mean value theorem or?
Mean value theorem.
Okay. So remember, MVT has two hypotheses. And this is a polynomial function, so f is continuous and also differentiable on the given interval. So I have to write here on -2, 2, on -2, 2 as a poly function. And then from 1 and 2 by MVT, there exists a C in the open, very carefully, open, which means C cannot be -2 or 2. Open interval, such that f prime of C equals f of B minus f of A divided by B minus A, where of course A is -2 and B is 2. On the side, I will find f of -2 and I will find f of 2. So I'll share my screen and I'll put it in the graphing calculator. I think I can safely finish with those. And I have x cubed. Oh, nope, nope. I have x, oh, I have x cubed minus 3x and plus 2. And all I want to plug in is this negative 2 and 2. And for negative 2 is 0, and for 2 is 4. Fine. Okay, so now I find f prime of x, which is 3x squared minus 3. I plug in c in it. So now this side is 3c squared minus 3. And this side is 4 minus 0 over 2 minus negative 2, which is 4. So then I have 3c squared. Do not go to the sides. This is an equation. You cannot simplify to the sides, please. An equation, one left-hand side, one equal symbol, one right-hand side. Minus 3 equals 1. 3c squared equals 4. C squared equals 4/3. Then c equals plus or minus the square root of 4/3. But I don't know if these fit in the interval negative 2, 2. I have to check. Since it's just a number, I'm just going to do this, the square root of 4 divided by 3. And I got 1.15. So c approximately plus or minus 1.15. Both belong to negative 2, 2. Both check. So in this particular case, for this function, we found 2 points guaranteed by MVT. And I have to show this piece. The problem is not correct without this piece, in which I say, yes, both work, or only one. And they cannot be the endpoints of the interval. C cannot be negative 2, it cannot be 2. Very good question. Thank you.